Hi guys, it's Kate. This video is a walkthrough of the first practice exponential gateway. Not only will I go through each problem and solve it out in full, but I'll also talk about important strategies and useful ways to go about solving problems that involve exponential functions. Let's get started. The first page of problems involves modeling with exponential functions, and you want to have under your belt a basic idea of how exponential functions work, how exponential growth or decay operates, and what that means, both how do you write down an exponential function that describes growth or decay in a particular situation, and then more general questions. Let's get started. A virus is growing exponentially, and initially there are V0 cells of the virus. That means just like some constant number to start out with. But every 4 days, the number of virus cells triples. Write a formula for the number of virus cells after T days. This is a straightforward example of needing to write down a function that describes a particular type of growth. Now, that doesn't mean that the actual process itself is very straightforward, but what you want to do is you want to take into account all of the pieces of information that have been given to you. First, you're told that you start off with V0 cells of the virus. So that means that when t equals 0, the number of cells you have is V0. Let's write that down in a convenient table to keep track of our information. Now, what else are we told? Every 4 days, the number of virus cells triples. So that means when t equals 4, when 4 days have passed. How many virus cells do we have? Well, if the number of cells has tripled, that means we have 3 times as many as we had before. So we should have 3 times V0. Now, what would happen 4 days after that? Well, that means that when t equals 8, the virus cells have tripled again. So we have 3 times as many as we had 4 days ago, which means we have 9 V0 virus cells at t equals 8. And you can continue filling out this table thinking, wow, if 4 more days went by, we'd be at t equals 12, and then we would multiply that number of virus cells we had by another factor of 3. So we'd have 27 V0 virus cells at this time. What's this table doing? It's going to help us write down our formula for the number of virus cells after t days, because we know that when t equals 0, our formula needs to return V0. When t equals 4, our formula needs to return 3 times V0. When t equals 8, our formula needs to return 9 times V0, and when t equals 12, our formula needs to return 27 times V0. So this table is a great way for us to check our answer at the end. Now let's think about what is going on with this function. Well, obviously it's exponential because every 4 days the number of virus cells triples. That's a constant percentage increase. And so what we want to do is we want to follow the basic exponential format. Here's how we wrote it in class. We'd have c times b raised to the x. Now, of course, what we're going to do is talk about what each piece of this is controlling and what it's reflecting, and then apply it to our particular problem. That c, that constant, is going to control for what the initial value is, because when you're plugging in 0 into an exponent, that b to the exponent is going to equal 1, and so c is all that's left over. So the c piece controls for whatever the initial value should be. The b piece, the base of the exponential function, is a constant that's chosen to represent the growth we're seeing in this problem. For us, this is a tripling. So for b, that's probably going to equal 3. In fact, it will equal 3. But in general, that b, the base of the exponential, is the constant that represents the growth that we're seeing. The exponent piece, well, the exponent involves the time variable in these growth and decay problems. And in particular for us, it tells us how often that growth that we're told about happens. So what does our formula look like? Well, that c that needs to control for the initial value, our initial value is V0. So our c is going to be equal to V0. Our b the constant that represents the given growth, well, our given growth rate is a tripling. So that means that our desired constant, or our base for the exponent, the exponential function, is going to be 3. And then our exponent needs to take into account frequency of growth. And that's when we zoom in on the fact that that tripling happens every 4 days. So what that means is that when our exponent is going to involve the variable t, and when t equals 0, we need to multiply v0 by 3 to the 0th power. Remember that 3 to the 0th power is 1. v0's just being multiplied by 1 here. When t is 4, 3 needs to be raised to the first power. When t is 8, 3 needs to be raised to the second power. When t is 12, 3 needs to be raised to the third power. By looking at that pattern, you should write down that our exponent is going to be t over 4. And this makes sense. If you plugged in 0, you'd just have v0. If you plugged in 4, you'd get 3 times v0. If you plugged in 8, you'd get 3 squared times v0, which is 9 times v0. If you plugged in 12, you'd get 3 to the third, or 27 times v0. And so this is our final answer. Let's take this approach down to number 2. Here we're told there are only 12,000 birds still remaining of a certain rare species of bird, and every 6 months the population of these birds declines by 8%. Write a formula for the population of birds after y years. Well, it's interesting to me that there are 2 bold words here, months and years. Given that our formula needs to be written in terms of years, we need to be very careful with how we make our table. The table is how we can basically check to make sure our formula that we write down at the end of this problem is giving us the important and relevant population levels for these birds. Let's go ahead and set it up similarly. We want y to be in years. We want it to map to a certain population of birds. Our first piece is just our initial condition, or the initial population level. When y equals 0, right now, there are only 12,000 birds still remaining. And then we're told that every 6 months, the population of birds declines by 8%. Well, since y needs to be in year units, that means every half a year, that decline of 8% will happen. Let's write down how many birds are left when y equals 0.5, or after 6 months. What have we done here? Well, we've taken 12,000 and multiplied by 0.92. Remember that we want to see how many birds are left after an 8% decline. Well, that means 92% will remain, and so that's why we multiply 12,000 by 0.92. Well, what happens after another 6 months? Well, our year timestamp will be at 1, and we'll take the number of birds from half a year ago and multiply it by 0.92 again, because we want to see another 8% decline. We now see that we have, after a year, 12,000 times 0.92 times 0.92, which is 12,000 times 0.92 squared. If we let another half a year pass, or another 6 months, we're at y equals 1.5, and we're going to take that initial 12,000 and we're going to multiply it by 0.92 3 different times, which means we're multiplying by 0.92 cubed. You can imagine that if we were at y equals 2, another 6 months in the future, we'd be at 12,000 times 0.92 to the 4th. In order to simulate that decline of 8%, we want to see what remaining 92% exists after each 8% decline. So this is a table that allows us to check to see whether our formula is giving us the right number of birds. Let's go ahead and try to write it down using the same approach that we did before. The first piece is going to control for the initial value of birds. Up here with the virus cells, it was going to be V0, because that was our initial number of virus cells. For us, our initial number of birds is going to be 12,000. So that's going to take the place of our C. Then we want to put in the exponential function. The base of the exponent has to be a constant that represents the given growth. In this particular case, it's not growth. It's going to be decay. For us, the constant that represents that decline by 8%, what we want to multiply in order to figure out what's left over after we've declined by 8%, that's going to be 0.92. And now we need to think about what we want to raise it to. Note that the exponent has to take into account the frequency of growth. For us, this is the every 6 months part. But since we are writing this formula in terms of y, or years, right, we need to think about how often that is in years. Well, if we're talking about every 6 months, that's going to be every 0.5 years. And that's going to control this exponent up here. It basically says, how often are you multiplying by 0.92? Well, we notice, looking back at our table, that when y is 0.5, 0.92 is raised to the first power up here. When y is 1, 0.92 is squared. When y is 1.5, 0.92 is cubed. When y is 2, 0.92 is raised to the fourth power. So the relationship between y and the exponent is that the exponent is twice as big as y. Let's write that in. And we can go back and double check. When we plug in 0 for y, are we getting 12,000? Yes. When we plug in 0.5 for y, are we getting a decrease of 8% or 92% remaining of the initial value? Yes. Are all of these individual values met as you plug in the relevant value for y? Yes. This is our formula for the population of birds after y years. Let's move along. These two questions are very interesting. They are general ideas and concepts around exponential growth and decay. Let's take a look. It says, suppose a radioactive isotope loses 20% of its mass every day. Which of the following is true? Over 4 days, it loses 80% of its mass. Over 4 days, it loses more than 80% of its mass. Or over 4 days, it loses less than 80% of its mass. Let's think about what it means to lose 20% of its mass every single day. Well, that means that if you start with something nice and easy to multiply by 0.8, remember, simulating that 20% decrease, how much is left over? I want to multiply by 0.8. Well, what if I started with 100 grams? And after a day, we have that 20% decrease. Well, 20% of 100 is 20. And so we're left with 80 grams after 1 day. Okay, let's lose another 20%. But now 20% is not another 20% of 100. It's 20% of what we have now, which is 80. 20% of 80 is 16. And so we end up with 64 after 2 days. Now that's interesting. The net change from the first day to the second was 20. The net change from the second day, I should say day 0 to day 1 was 20. Day 1 to day 2 was 16. And you can imagine that if I were going to take another 20% off of 64, this raw amount right here would get even smaller, right? It doesn't stay at 20 because we're losing 20% of what's left over. And since what's left over is even smaller than the initial value, it's not going to be a constant loss of 20 grams every day. It's only going to be 20 grams that first day, and then we need to calculate a 20% loss of that now diminished quantity. So what ends up happening is that we will actually be losing less than 80% of its mass. What's another way to figure this out? Well, if you want to simulate that loss of 20%, you know you're multiplying by 0.8. In order for that to happen 4 days in a row, you're going to multiply by 0.8 4 times, resulting in a total multiplication of 0.8 to the 4th. If we can figure out what 0.8 to the 4th is, we could determine what the total multiplying factor would be and therefore what the total percent loss would be. If you take 0.8 and multiply it by itself, you'll get 0.8 squared, which is 0.64. If we take 0.64 and multiply it by itself, we will get 0.8 to the fourth. So let's do that, and we'll be able to get an exact value for 0.8 to the fourth. All right, I got seriously old school up here and just did straight up multiplication. And I ended up with 0.4096 as what 0.8 to the fourth is equal to. All right, well, if I'm multiplying something by 0.4096, multiplying by 0.4096 is what percent decrease? It's about a 60% decrease, not an 80% decrease. So you can see that, yes, our intuition over 4 days, the isotope loses less than 80% of its mass is true. This is because we're not losing 20% of the original value every day. We're losing 20% of the already diminished value after each day. And so that first initially large decrease doesn't keep up. It doesn't maintain. It's not just 4 times that amount is what we end up losing. It's less than that because you're taking 20% of a smaller and smaller value every day away. And so its total is not going to be 4 times that. It's going to be slightly less than 80% is lost overall. Let's take a look at the second problem. It says a credit card has a 24% annual interest rate. This means your balance grows by 2% every month, your balance grows by more than 2% every month, your balance grows by less than 2% every month. Well, note that the result that we got from part 1 of this problem said that if we are losing 20% daily, overall, we lose less than 80% over 4 days. Let's think about what that would mean if it were growth, which is in this particular credit card interest question. So what if we were growing 20% daily? And I realize I'm talking about a different problem now than the one that's in front of us, but bear with me. If instead of losing 20% daily, we gained 20% daily, how much would we gain overall in 4 days? More than 80%? Less than 80%? Let's do this little table again where we start with 100. If we gained 20%, how much will we have? Well, we increase to 120, right? We're multiplying by 1.2 if we gain 20%. But then what happens if we gain 20% from there? Well, 10% of 120 is 12, so 20% is 24, so we'd actually gain 24. So we see that actually the opposite thing is happening as with decay. Initially, we only gained 20, but then when we said, okay, there's 20% growth on this now larger number, then we gain 24, and that will continue happening. So our net gain over 4 days is not going to be just 20 times 4. It's actually going to be more than 20 times 4. So we know that if we gain 20% daily, we'll gain more than 80% overall in 4 days. So now the question becomes, hey, what if overall you have a 24% annual interest rate? What would that mean? Well, if we had a 2% growth every month, if we gained 2% every month, overall, we'd have more than 24% every year, right? 2 times 12. So that means if we need exactly 24%, we actually need our balance to grow by less than 2% every month. This is because, remember that every month we're taking a 2% increase on what is now a larger value again and again and again. So if that growth was happening at 2% every month, we'd actually end up with more than 24% growth in a year, which means that if we want to hit exactly 24% growth in a year, we need to be growing by less than 2% every month in order for the net effect to be exactly 24%. Let's take a look at the next page. We begin with problem 4, which is an exercise in algebraic manipulation of exponential functions. And it says if we write the exponential function y equals 3 times 3 to the 2t minus 1 in the form y equals p times q to the t, what is p and what is q? So the real difficulty is going to be to isolate t up there in the exponent. An important thing to do is to re-express 3 as a power of 3. So we know 3 by itself is just 3 raised to the first. We also know that if you have the same base shared between two exponential functions, in this case our shared base is 3, and we have a product between two shared bases, then in order to combine it into one term, we keep the base the same, but we add the exponents together. Interestingly enough, that 1 is countered by a subtraction of 1, so we're left with just 3 to the 2t. And our desire is to somehow find that is equivalent to some constant just raised to the tth power. Well, what's interesting about this now is that we have a product up in our exponent, and one thing that we know about products in exponents is this exponential property. That if you have a particular base raised to one exponent, and then you take that exponential and raise it to another exponent, the net effect is to take the original base and raise it to the product of both those exponents. And because multiplication of real numbers is commutative, note that this could be an equivalent rewriting of x to the b raised to the a, because that would be equal to x to the b times a, and both of these are equivalent. So all three of these, this, they're all equal, which means that we can re-express this as 3 raised to the second power, all of that raised to the tth power, because that would result in the product that we just came from in the previous step. Now, of course, 3 raised to the second power is just fancy for 9. And we're pretty much done. Note that in this format here, that means for us, p is equal to 1, right? This entire thing is being multiplied by 1, and q is equal to 9. And those are our final answers there. Let's take a look at number 5. We're told that we need to sketch the graph of 2 times 2 minus x minus 4, and that can be very overwhelming. But let's start with the simplest version and then use a bunch of graph transformations to get us from a simple exponential function to the one that we're actually trying to find. I think a good jumping off point is 2 to the x, and I'm going to do a small sketch over here on the side. Now if we start with 2 to the x, what does that look like? 2 to the x looks something like this, right? This point right here is 0, 1. This limit goes to 0 over here. It has a horizontal asymptote at y equals 0, and then it goes up to infinity on the right-hand side. But of course, we don't have 2 to the x. Now let's start manipulating it a little bit. What happens if we take 2 to the negative x? Now remember, when you fiddle with the input in there, you're doing something horizontally. When you multiply x by -1 every single place, what you're doing is a horizontal reflection. So a reflection about the y-axis, which means that if we were about to write down 2 to the negative x, which is also 1/2 to the x, a fair statement if you're looking to make that, 2 to the negative x, what you now have is something that looks like this, right? And now that point is still there. Note that the y-intercept has not changed. Still 0 and 1. Now let's get a little bit more complicated. The next thing we want to do is we want to multiply by 2. That is a vertical stretch. Recall that if we had had any x-intercepts, those would have stayed in the same place, but it's the function value that's now being multiplied by 2. So you have a bit of a steeper movement vertically. The last piece before we draw this for real is subtraction by 4. That's a vertical shift, and that's what's going to give us our final graph. So we want a vertical shift downwards by 4 units, which means that that horizontal asymptote is now going to go down to y equals -4, but otherwise everything else stays the same. So I've drawn in our horizontal asymptote, and since everything's shifted down by 4, we can draw it in. That wasn't the greatest movement of mine. Let's try that again. Draw it in. There we go. And this particular point right here has now shifted down by 4. It was at 0, 2. It's now at 0, -2. And then we need to figure out what this point is right here. And note that even though this asked me to label asymptotes and intercepts, I was able to make my life a lot easier by tracking one of the intercepts throughout the course of the problem. So I have the y-intercept done. I just need to figure out the x-intercept. Let's go ahead and do that. Note that the x-intercept is where the function value is 0. So I'm going to plug in 0 for y and then figure out what x needs to be in order for that to hold. Let's go ahead and solve this. We're going to add 4 to either side and then divide by 2. And this is about as far as you actually have to go, because on the left-hand side we have 2 raised to the first power. On the right-hand side we have 2 raised to the negative x power, which means that since the bases match, the exponents have to match, since these are the only terms on either side of the equal sign. And so that means that negative x has to be equal to 1, which means that x is equal to -1, and that makes sense on our graph. So this is going to be -1, 0. It also says label one point that is not an intercept. You can pick whatever you like, but I guess I'm going to pick +1 because that seems like the easiest place to start for me. So I'm going to label it 1 and then plug in 1 for x to figure out what y should be. So y is equal to 2 times 2 to the -1 minus 4. Well, 2 to the negative first power is just 1/2. 2 times 1/2, right? So I have 2 times 1/2 minus 4. 2 times 1/2 is just 1, so I have 1 minus 4, which is equal to -3. And that makes sense based off of my graph here too. Always want to make sure that you're getting negative things out where you think you should and positive things where you think you should. But that is a nice way to sketch the graph of an exponential function. Number 6 is a similar skill. Let's take a look. I'm also going to add, for the sake of clarity, that the move from this to this was a vertical shift, because what we're about to do is work from the picture to the function. So now we're taking a look at this, and we want to use all these different graph transformations to try and figure out what y equals a times bx plus c is going to be equal to. As you can tell from our experience above and your experience on the problem sets, this piece right here corresponds to a vertical shift, and if that exists, which it does in this particular case. In this particular case, we have a vertical shift upwards by 3, so c is 3. What's interesting to note then is, what does this function look like if we unshifted it, if we moved it down? That can make a and b much easier for us to figure out. So I'm going to draw a little drawing over here of what it would look like if I just shifted it down by 3. And it would look something like this. And the 2 points on here, well, that means that this point right here would move down by 3. So we'd be at 0, -2. If I move down by 3. And this point right here, which used to be at -3, that's shifting down by 3, so that should be at 1, -6. So what am I seeing overall? Well, I'm seeing that if I'm now totally ignoring this shift entirely, this is just isolating a times b to the x pieces of this particular function. So for me, this a is what's happening when x is equal to 0. Well, if x is equal to 0, b to the x is just 1, and a controls the entire function value if x is 0. So that means that a has to equal -2 in order for me to be able to plug in 0 and get out -2 right here. So that means a is equal to -2. Then I have that, oh, when x is 1, we have -6 coming out of this entire thing, which means that -2 needs to be multiplied by 3. How do I know that? Well, if I say that -2 times b to the first power equals -6, and I divide both sides by -2, and the way I did this was by plugging in these particular function values. Note that this is x is 1, y is -6, so x is 1, this should produce y is -6, and so I have, okay, divide by -2, I now have b equals 3. And so this tells me that, oh, this abx is -2 times 3 to the x. I unshifted this so that this algebra would be much more polite. And so I was able to, once you notice that C alone controls the vertical shift, undo the effect that C has, and then it allows you a really crystal clear look at what A and B are doing, then put that all together, and your final answer becomes that my y equals -2 times 3 to the x plus 3. And that's it. One piece at a time. Let's move on. The remaining exercises are testing your ability to understand the properties of exponents. I'm going to put a couple at the top here. One is that, one we've already touched upon, which is that if x is raised to the 8th power and x is raised to the bth power, then the result is x raised to the a plus bth power. That's because you have a total of a plus b factors of x if you're multiplying a factors of x times b factors of x. Now, if you have x to the a divided by x to the b, meaning shared base, different powers, one is divided by the other, then you have subtraction between the two. And then the last piece is what we've already discussed, which is that x to the a, all of that raised to the b, is equal to x to the ab, which is also equal to x to the b raised to the a. All right, let's get started. We're going to use all of these in what we're about to do. The first task is to simplify this as much as possible. And because everything in the numerator is over a b to the x in the denominator, I have a hunch that what I want to do is isolate b to the x in as many terms as I can. Let's get started. First, I want to do that in b to the 2x. Now, I notice that that's a product, so I'm going to exploit this idea, that I can separate this out as something raised to the 2, then raised to the xth power, or something raised to the xth power and then raised to the 2nd power. I prefer isolating b to the x. So I'm going to re-express b to the 2x in the following way. I'm going to say that this is equal to b to the x, all of that raised to the 2nd power, right? Because this is equal to the same base raised to a product of the exponents. I'm then going to take a look at this term right here. B to the x times b to the x is an example of this rule up here, where you have the same base, two exponents, and the result is keep the base, sum the exponents. So what this is b to the 2x, which is identical to the first term, actually. So this is b to the 2x. And so I have another example of b to the x quantity squared. Slightly different here with the b to the 3x. I want to take b to the x and cube it, because that would create the base b to the 3 times x power. And then this right here, well, this is the cube root of b to the x, all of that raised to the 6th. And so the cube root is raising everything underneath that weird radical sign to the 1/3 power. So that's really b to the x to the 1/3 power, all of that raised to the 6th. Here we want to exploit that property by taking the product of the exponents between 1/3 and 6. This is really b to the x raised to the 2nd power. And we have the same thing as our first two terms there. So we have b to the x raised to the 2nd power. All of that over b to the x. Now we have a lot of common factors. b to the x appears in every single term, but there are going to be factors of b to the x left over. We want them to drop out of every term. That's the only way that we can ever cancel anything. So it cancels from there. It cancels from the first term, but there is still one term of b to the x left over. Let me change the color that I'm writing in so it's much clearer. There we go. Cancels from the second term, but still one term left over. One term cancels from the third term, but there are still two terms left over, and one cancels from the last term. So I am left with b to the x plus b to the x minus b to the x quantity squared plus b to the x. All right, well, I have three like terms here. I have b to the x plus b to the x plus b to the x. Well, that's 3 times b to the x. So I end up with 3 times b to the x minus b to the x quantity squared, and that is as simplified as it gets. Can't go any further. And you could, I mean, ideally you could re-express this if you really wanted to get rid of parentheses. You could call that b to the 2x, but there's nothing more that cancels. So our final answer is going to be 3 b to the x minus b to the 2x. Done. Let's try this again in number 8. All right, let's take a look. We have this crazy expression. We want to simplify it. Lots of exponents are in our way. The first thing we notice is that if we have a product of exponents, such as here, a product, pardon me, and it's all being raised to the 2x power, that 2x is acting on both of these terms in the product. That means not only are there 2xa factors, but there are 2xb factors. What do I mean by that? I mean that if I had something like ab cubed, what that equals is ab times ab times ab, which is the equivalent of a times a times a times b times b times b, which is the same thing as a cubed times b cubed, meaning that there are 3 factors of a that show up, there are 3 factors of b that show up. The same thing is happening here, except that it's just 2 times x numbers of factors. So here, let's rewrite that. We're going to say that this term here is equal to 2 times a to the 2x times b to the 2x. Now, when we're looking at something like a over b, this is still distributing as well. We're multiplying by 8 times a to the 2x over b to the 2x. Why does that happen? Well, let's think about that. If we had a over b and we cubed that, that is a over b times a over b times a over b, or a times a times a over b times b times b, or a cubed over b cubed. All right, so we've been able to separate out just this first term, separate out everything that's in the parentheses and raise every term in the parentheses to the appropriate exponent. What we notice right away is that there's a common factor of b to the 2x that appears in both terms here in the product. So we can cancel those two. And we end up with a to the 2x times a to the 2x, and then 2 times 8. So we end up with 16, same base, different exponents, so, or I get really same exponents, but you sum the exponents. So we have 16a to the 4x. That's just from this piece here. So we have 16a to the 4x. Now let's tackle this second piece. So here I want to take a look at what's happening in this numerator. I'm going to distribute that a to the x across both terms. So I end up with a to the x times a to the x plus a to the x times 4a to the 2x. Then I want to subtract off 4a to the 2x distributed over both terms. So I have minus 4a to the 2x times a to the x minus 4a to the 2x times 4a a to the 2x. That negative sign needs to distribute with both of these. And that is all over e to the x times a to the x. Whew, my goodness. Okay, so let's see here. I have a to the 2x in this term, so I'll rewrite that. A to the 2x plus a to the x times 4a to the 2x. So I have plus 4a to the 3x, because I can combine those two like terms. Then minus 4a to the 3x. Ooh, that's exciting. And then minus 16a to the 4x, and all of that is over an a to the 2x down in the denominator. We see right away that this plus 4a to the 3x minus 4a to the 3x cancels, and I'm left with a to the 2x minus 16a to the 4x all over a to the 2x. So let's get a clean writing of this. I have 16a to the 4x plus a to the 2x minus 16a to the 4x all over a to the 2x. So I have a common factor in each term in this second fraction here. I have a to the 2x appearing everywhere. So I have a to the 2x appearing here. I also have a to the 2x appearing here. And I also have a to the 2x appearing in here, but if I cancel out 2x, I'm left with 2x, right? Because 4x minus 2x leaves 2x. So what I'm left with as my final answer is 16a to the 4x plus, note that in this term 1 is left over, minus 16a to the 2x. If you're wondering again how we were left with 2x right here, that's from the fact that if you have 16a to the 4x over a to the 2x, you have the same base, different exponents. You want to subtract 2x from 4x. So this is going to be 16a to the 4x minus 2x minus, there we go. And so you're left with 16a to the 2x. But that's our final answer there for that particular problem. Let's move right along, our final page. Our final two problems are a simplify as much as possible again. So let's get started. We're diving right in here, people. Okay, here we have 2 to the x minus 1 quantity squared minus 2 to the x plus 1 quantity squared times a to the negative x times 2 to the x minus 1. Already I'm seeing so many common bases that I know the best approach or plan of attack is to expand this stuff that's inside here that's being squared and then see what I can combine with other things. All right, let's take a look at what happens here. The very first component, that 2 to the x minus 1 quantity squared, let's expand it. What I'm left with then is 2 to the x quantity squared minus 2 to the x times 2. And note that that's a product of 2 to the x, negative 1, and 2. This is part of our expansion. And then negative 1 quantity squared. Then I want to subtract off the expansion of this. And I want to be very careful because I see that negative sign out in front. And so I need that to distribute across all the terms. That means I have 2 to the x, all of that squared, plus 2 times 2 to the x times positive 1 plus 1 squared. And then out here I have the times, that whole thing, right, is times a to the negative x times 2 to the x minus 1. Okay, I haven't touched those last two terms in the product quite yet. All right, let's get this going here. I have that first term, 2 to the x quantity squared. The result is going to be 2 to the 2x. We're pros at that by this point, that if you're taking an exponent and raising it to another exponent, the result is the product of those two. Then if I have 2 times 2 to the x, really this is 2 to the first power times 2 to the x. So same base, different exponents. I want to subtract off now 2 to the x plus 1. And then negative 1 squared is just 1. Then I'm subtracting. Here I have 2 to the x squared, so that's another minus 2 to the 2x. I have 2 to the first times 2x. So that's another 2 to the x plus 1, but I'm subtracting it because that negative sign is distributing. So I have x plus 1. And then I have plus 1 inside here, right there. But I also have another negative sign because that exponent, the negative sign is distributing. So in total, everything inside here looks like that. And then times 8 to the negative x times 2 to the x minus 1. All right, let's start looking at how to cancel some things out or combine some things. So I have 2 to the 2x minus 2 to the 2x. These two things cancel right away. I have plus 1 and minus 1. Those two things cancel right away. And so I have minus 2 to the x plus 1 minus 2 to the x plus 1. All right, so I feel like I have minus 2. I don't feel like I have. I know that I have 2 times minus 2 to the x plus 1. And of course, those other two terms are still on there. I haven't touched them at all. Now, let's take a look here. Note that this is really 2 to the first times negative 2 to the x plus 1. And so this can be combined here, these two terms right here, could be negative 2 to the x plus 2. So I've rewritten that. Note that this negative sign, you might be a little bit confused about that. That's just the equivalent of saying negative 1 times 2 to the x plus 2. So that negative sign is sort of trailing us through the various steps from here to here. Now you might think, oh, I want to combine the two pieces that have 2 as a base and leave the piece that has 8 as a base alone. But in fact, 8 is a power of 2. 8 is 2 cubed. So let's rewrite that as a power of 2 as well. So we can say this is negative 2 to the x plus 2 times 2 cubed to the negative x times 2 to the x minus 1. And so all of a sudden, hey, we have 2 cubed raised to the negative x power, so we could just rewrite this as negative 2 to the x plus 2 times 2 to the negative 3x times 2 to the x minus 1. And suddenly we have 3 bases that are all the same, all 2, with different exponents, so we can sum those exponents. That negative 1 factor just keeps trailing because it's just a sign, right? It's just another factor of negative 1. So we have negative 2 to the x plus 2 minus 3x plus x minus 1th power, which is completely ridiculous and not simplified at all, but we certainly can get there. So we have negative 2. X minus 3x is negative 2x plus x is negative x. So I have negative x plus 2 minus 1 is plus 1, or you could write that as negative 2 to the 1 minus x, whatever you like. This is your final answer. Celebration! And we go on to our last problem. Simplify as much as possible. All right, we have a lot of things under square roots, which is raising things to the 1/2 power. We have a cube root over here, which is raising it to the 1/3 power. We have a 4th root down here, which is raising it to the 1/4 power. Let's get this all under control and first raise this quantity to the 1/2 power, this one to the 1/3 power, this one to the 1/4 power, this one to the 1/2 power. Let's rewrite that right now. Right away, we can see how some of these powers start to simplify, because if we have something raised to the 4m power and then raised to the 1/2 power, the result is raising it to the exponent 4m times 1/2. So this right here is going to become 2m. The same thing happens right here. This will become 3m. The same thing happens here. We have to be careful because that 1/4 needs to distribute across that entire difference. So we have m minus 2. And then we can actually simplify a little bit right here because 1/2 times 2 is just 1. And so what we end up with is 3 to the x. So we can go to our second line of computation. So we have 3 to the x, that's left alone, times x to the negative 3m, times x to the 2m, times x to the 3m. All of that goes over x to the now m minus 2, because that 1/4 distributed across 4m minus 8, times x times 3 to the x. And we see a factor of 3 to the x in both the numerator and denominator. And we see a couple of other things. One thing that I see is I'm trying to sum all the exponents across the same base. So up here in the numerator, I have x to the negative 3m plus 2m plus 3m. So I end up with, this is x to the negative 3m plus 2m plus 3m. And of course, even in there, these two guys will cancel, so we just have x to the 2m up there. Then we have x to the m minus 2 times x to the first power, so I have x to the m minus 2 plus 1 down here. So I have m minus 1. This entire thing becomes m minus 1. And so we go down here and we're like, okay, I have x to the 2m over x to the m minus 1. So we're left with a quotient of two exponents that have the same base but different exponents. So what we want to do is maintain the base and take the difference between these exponents. So this equals x to the 2m minus, and in parentheses, m minus 1, because that negative sign has to distribute between the m and the 1. So what we end up with is x to the 2m minus m plus 1. We get our final answer, which is that is x to the 2m minus m is just m, and then the plus 1 stays. And that is our last solution. Oh my goodness. If you have any questions at all, please don't hesitate to ask. Go slowly, methodically, and develop a nice fluency and facility with the properties of exponents.